what the Pythagorean theorem says is if you have a right triangle, and a right triangle is just a triangle where one of the angles, one of the interior angles of the triangle is 90 degrees. Then we'll label the side lengths A and B, and the side that's opposite the right angle, the 90 degree angle, we call that the hypotenuse, and we'll label it C. And it always happens, always, that squaring the side lengths and adding them up gives you the length of the hypotenuse squared. And everybody knew this, right? The Pythagorean theorem today is named after the Greek mathematician Pythagoras, ancient Greek guy, 500 BC-ish. But it wasn't just the Greeks. In fact, the Greeks were kind of late to the game because a lot of ancient civilizations knew about this, right? Like separately, independently of each other, they weren't communicating, but like the ancient Aztecs knew about this, the ancient Mayans knew about this, the ancient Chinese knew about this, the ancient Indians knew about this, ancient tribes in Africa knew about this. Everybody across the world kind of figured this out, you know, between like 1000 BC and 5000 BC. It's kind of around then. The reason we know that they figured this out, even though there's not like textbooks from 5000 BC, the reason we know that they figured this out is because we would find like a stone slab in like a Mayan temple, for example. And on the stone slab, they've got like etched out like 3, 4, 5, and maybe tally marks. And that's not that interesting, right? Because those are consecutive numbers. But then on the next line, they might have 5, 12, 13. And that is interesting, right? That's the second Pythagorean triple. So a Pythagorean triple is a set of 3 numbers that are natural numbers that satisfy the Pythagorean theorem. Like 3 squared plus 4 squared is equal to 5 squared, but also 5 squared plus 12 squared is equal to 13 squared. And not just this, but this stone tablet might have like 20 or 30 rows of just Pythagorean triples. And there's no way you can make that without knowing the Pythagorean theorem, right? So we have evidence like this all over the place for different ancient civilizations coming up with this. And so the next thing I want to show you is how do we know, and how did all the ancient peoples know that this relation is always true for every right triangle? And the proof goes like this. You start by drawing a box. Specifically, I mean, you start by drawing a square. So these side lengths all have equal length, and there's a 90-degree angle in all of the corners. That's what makes it a square. And the next thing we're going to do is start from this corner and either use a ruler or like a little length of string or something with a fixed length. And we're going to measure some length out onto the side of the square. And use the same ruler, the same rope, to mark the same spot, that same distance away from each of the corners. We'll call that distance lowercase a. And since every side length is the same length, that means what's remaining is also the same length. And we'll call that length lowercase b. And what we do next is we connect the dots. And the prerequisite to kind of understanding this proof is a theorem of geometry you might have heard before in like 10th grade. It's called the side angle side theorem. And what the side angle side theorem says is if you've got a triangle with a particular side length a particular angle measure and another side length on either side of the angle. And that matches exactly the side angle side of another triangle, then those two triangles must be congruent. So all four of those triangles are exactly the same triangle according to the side angle side theorem, which means this side length is the same for all four triangles. And that means that the angle between B and C is the same for every triangle. I'll call that theta. And the angle between A and C is the same for every triangle. Let's call that phi. But those are all the same. Now, what do you know about the interior angles of a triangle? If I were to add together all three interior angles, what does that have to equal? 180 degrees. Okay? So if I take away the 90 degree angle, I subtract 90 degrees from both sides, phi plus theta has to be 90 degrees. The next question I have for you is, if you've got a situation like this, where on the bottom I've got a straight line with some other lines coming in and out, that gives me three angles. And if these angles are phi and theta, and there's a third angle here, what do these three angles have to add up to in order to complete the straight line? Yeah, those three angles that are incident on a straight line have to add up to 180 degrees. And that means that this angle here in the middle has to have an angle measure of 90 degrees. Because phi and theta add up to 90. The three angles together add up to 180. And so that means these interior angles of this shape are also 90 degrees. So what we just learned is that the shape in the middle is a square, because the side lengths are equal and the corners have 90 degree angles. Now, we're getting to the good part. If I want to calculate the area of the big square, the one I drew to begin with, the area of the big square is equal to A plus B squared. A plus B is the side length of the big square, and if you want the area, you take the side length of the square. There's another way I could calculate the same area. I'm calling it the area of the big square. And the other way I could calculate this is I could start with the area of the little square in the middle. We call that C squared to the area of the middle square. And then I would add to that the area of the four triangles. What would be the area of one of those triangles in the corner? So the area of any triangle is 1/2
half base times height divided by 2.
Yeah, it's base times height divided by 2, or you can think of it as 1/2 times the base times the height. So for this triangle right here, they're all the same, but the base is A and the height is B. So when I add 4 times 1/2 A times B, that's just the area of all four triangles. But these are the same thing calculated in different ways. So I could write A plus B squared equals C squared plus 2AB. Both the left side of this equation and the right side of this equation are the same because they are both the area of the big square. And the only thing I did is I multiplied 4 times 1/2 to get 2. On the left side, this expands as this. Okay? What I mean by expands is if I want to multiply a plus b squared, that's a plus b times a plus b, right? And you can think about foiling if you're comfortable with foiling first, outer, inner, last. Or another way I like to keep track of my work so that I don't, lose anything is I multiply a plus b times a plus b. And the corners are plus ab plus ab. And whenever I add all of this together, I would get an a squared plus 2 copies of a times b plus b squared. So that's what I mean by expand the left side of the equation. Now, on the right side of the equation, I've got c squared plus 2ab. And do you see anything that appears on both sides of my equation that I could just cancel out? Yeah. I'll just subtract 2ab from both sides of my equation to keep everything balanced. And then what I'm left with is the Pythagorean theorem. And I could always choose to start off by drawing a big square of different sizes. And I could always choose that side length a, lowercase a, to be any amount across the side length. And so regardless of what right triangle you want to make, we can definitely make the Pythagorean theorem work. And we know this is always true for every right triangle because of that proof. This is how all of the ancient civilizations across the world knew that this equation had to hold for every right triangle, is because they could get a stick and they could draw this in the sand and they could compare it with each other. Okay. Now, moving on. We would say the square root of 25 is 5. And we say this because 5 squared is 25. But what would be the square root of negative 4?
2.
Yeah, the important thing, and some of you already have seen this before, but this is not a real number. It can't be a real number because what we would be looking for is like some number squared equals negative 4, right? That's the definition of how the square root works. And the problem is any real number is either positive or negative or 0. But if you take a positive number and you square it, it's positive. And if you take a negative number and you square it, it's positive. And 0 squared is 0. So there's no real number where I could square it and get a negative number. That means the square root of any negative number cannot be a real number. So what we do instead is we say, well, if this is not a real number, we have to make up an imaginary number. And we start off by saying the square root of negative 1 is going to be called lowercase I. And then if I want the square root of negative 4, negative 4 is just the same thing as negative 1 times 4. And that would be the same thing as the square root of negative 1 times the square root of 4. Because I told you before, we can actually separate a square root if we're only multiplying in the radicand. And now, the square root of negative 1 gets to be called little lowercase I because we said so. And the square root of 4 is just 2. And the standard way to write this is to write the 2 first, and we call it 2i. Some of you have already seen this, because I heard some 2i's as my answer to the question before. But that's how we're going to do things. The lowercase I is just a shorthand. It saves you a little bit of money each year on buying ink for your pen if you write the lowercase I instead of square root of -1. But it means the same thing. And that's how we decided to handle the square roots of negative numbers. Now, if I had I squared, that would be -1, because this would be the square root of -1 squared, and the square would cancel with the square root. And that means I squared is -1. What if I have I raised to the power 3?
Still 1.
This is the same thing as if I had I squared times I, because both of those is just I times I times I. But I squared is -1, and so I cubed would just be -I. If I have I to the 4th power, that would be what? That would be the same thing as +1. Because I to the 4th power is just I times I times I times I times I times I times I, 4 times, right? And that's the same thing as I squared times I squared. Only I squared is -1. So this is -1 times -1 gives you +1. All right. What about I raised to the 5th power?
Square root of
This is exactly like having I to the 4th power times I. I to the 4th power, we just said, is the same thing as the number 1. And so I to the 5th power is the same thing as I. And I'm going to do I to the 1 power, just for the sake of completeness. This would be just I. The 1 power doesn't change anything. The 1 power never changes anything, so that's just I. What if I have I raised to the power 6? Perfect. It would be the same as I squared, which is -1. And what if I have I raised to the power 7? Yeah, it would be the same as I to the 3rd power, which is -I. And what if I have I raised to the 8th power? That's just I to the 4th times I to the 4th, which is 1 times 1, which is 1. Here's the pattern that you need to recognize. It goes I, -1, -I, 1. And then it restarts. It's a 4 cycle. So it goes I, -1, -I, 1. I, -1, -I, 1. And without having to do any work, you know that I raised to the powers 9, 10, 11, 12 would have to be I, -1, -I, 1, right? Pattern just goes on forever. All right. So here's a question. What if I had I raised to the power 2001? Yeah. That is just I raised to the power 2000 times I raised to the 1 power. And the thing is, when you've got the power 2000, 2000 is a multiple of 4. And as long as it's a multiple of 4, it's just the same as a positive number 1. And so that's how we reason about these things. If I tell you I raised to some power, you just have to look for the smallest, not the smallest. You look for the largest multiple of 4 that is still smaller than 2014. Subtract that away, and then you see what you have. Okay? So what's I raised to the power 2014?
I to the power 2012 times I squared.
Yeah, exactly. And I squared is just -1. We'll do one more and then we'll move on. What's I raised to the power 1993? '92 is going to be the next power of I that's just barely smaller than. It's a multiple of 4, but it's just barely smaller than 1993. And so that's just I. All right. So here's the new game. What if I have I raised to the power 0? It's 1. Because anything raised to the power 0 is always 1. That's true for anything. What if I've got I to the -1 power? So the negative exponent tells you to take the reciprocal, right? But if I were to take 1 over I and I multiply by 1, that doesn't change anything, right? Multiplying by 1 doesn't change anything. So let me just go ahead and multiply by 1. I to the 4th power is 1. And 1 divided by I times I to the 4th power, you know, that's just in case anybody needs to see this written out. Sometimes it helps to solidify a concept. That's I to the 4th power, and this is 1 over I. I can cancel out one of them, and we find out that this is the same as I to the 3rd power, which is the same as negative I. What if I had I raised to the power -2? That would be the same thing as 1 over I squared. And I can also multiply by I to the 4th because that doesn't hurt anything. And when that cancels out, 4 minus 2 is 2, and I squared is just negative 1. So I to the negative 2 power is negative 1. Next, we've got I raised to the power negative 3, which is like 1 over I to the 3. And it doesn't change the value if I multiply by I to the 4th, and that's the same as I. I raised to the negative 4 power is 1 over I to the 4th times I to the 4th. The negative exponent tells you to take the reciprocal. I am choosing to multiply by I to the 4 because it's the same as multiplying by 1 and it just won't change it. So that's fine. And this is just 1. But if you don't want to remember that and do the work every time, another thing you could remember instead is that this follows the same pattern. If I've got I to the 0 power, that was 1. And if I have I to the power negative 1, that is negative I. And if I've got I to the power negative 2, that was negative 1. And if I have I to the power negative 3, that was I. But again, I'll zoom out so you can see the bigger pattern. We have going up 1, negative I, negative 1, I. And continuing to go up, we have 1, negative I, negative 1, I. So the pattern goes the same, and whether you're increasing powers of I or decreasing powers of I into the negative numbers, it still works, it still holds. Same pattern. Okay. What's I raised to the power negative 2001? Since 2000 is a multiple of 4, we don't have to worry about it. I raised to the power negative 2000 would just be positive 1. And I to the negative 1 is negative I. And so this is just negative I. Okay? So the big takeaway here is that powers of your imaginary unit I, they go in a 4 cycle. And that continues forever and ever. It's a little bit weird, but that's how it works. Okay, if we talk about the set of imaginary numbers, the set of imaginary numbers is just any real number times I. So like 6I, that's an imaginary number. A complex number is denoted with a double struck C for complex. And a complex number is any number that has both a real part and an imaginary part. So let's say my number Z is a complex number. I can have a real part and an imaginary part. I would say that the number negative 3 is the real part of Z, and 7I, that's the imaginary part. But Z altogether is one complex number with a real part and an imaginary part. if I want to draw a Venn diagram, again, we'll start where we started before, where we've got the natural numbers. And that's the set of numbers 1, 2, 3, 4, on and on and on. And sometimes including 0, depending on the context. Then we had our set of integers. And integers contained all of the natural numbers. The integers always contain 0, and we get the negative numbers too. The negative natural numbers, that is. When we had the rational numbers, we said the rational numbers contained all of the integers and also contained fractions and any number that could be represented as a fraction. Then we said the real numbers, that's a set of numbers that's even larger than the rational numbers, because the real numbers also contain the irrational numbers. And irrational numbers are still important because it contains stuff like square root of 2, square root of anything that doesn't end up being an integer, and also pi, for example. And then now we're talking about the complex numbers. The complex numbers actually contain all of the real numbers, because if your complex number just has 0 as the imaginary part, then your complex number is a real number. But complex numbers also contain the imaginary numbers and also contain any number that's just non-real. Any number that has a real part and a non-zero imaginary part. So this is our big Venn diagram, and this is where we're going to conclude our Venn diagram for this class. That's our Russian nesting doll of number sets. You can still add, subtract, multiply, and divide with complex numbers. Like, if I want to add these two complex numbers, where A is 5 minus 12i, and B is 7 minus 3i, the number A plus B, we can find it, we can add, where we just add the real parts and imaginary parts separately. So A plus B is going to be 5 plus 7. And negative 12 plus negative 3, what would that be? Negative 15. So notice I added the real parts and then separately added the imaginary parts. That's how you add complex numbers. Subtracting complex numbers works the same way. You just subtract the real parts separately, and you subtract the imaginary parts separately. So if I want to subtract A minus B, that would be 5 minus 7, negative 2. And then, separately, I consider the imaginary parts. What is negative 12 minus negative 3? That would be negative 9. And that's how you subtract two complex numbers. Any questions? Hopefully that makes sense. Hopefully that's exactly the way you would expect addition and subtraction to work for complex numbers. And we will move on to multiplying real quick. Multiplying is not as straightforward, but it's still not terrible. This might be the same numbers. Oh, that's where it says subtract. I think it may still be the same numbers if I say multiply. So, yeah, multiply now. If I want to multiply, I get 5 minus 12i times 7 minus 3i. I'm going to choose to multiply these things by drawing a box where the top side length is 5 minus 12i, and this side length is 7 minus 3i. And we just have to find the areas of the little boxes and add them together to get the area of the big box. 5 times 7 is 35. 5 times negative 3i is going to be negative 15i. Negative 12i times 7 is going to be negative 84i. Then negative 12i times negative 3i is going to be positive, two negatives make positive, 36i squared, because I've got I times I. This is going to be 35 minus 36 minus 15i minus 84i. Can somebody tell me, why did I write 35 minus 36?
Because I squared equals -1, so that just changes the sign part of it.
Yeah. Whenever I'm multiplying two complex numbers like this bottom box is always going to end up with an I squared, because you've got the two imaginary parts that both contribute one of the i's. But I squared is -1. And so 36 times -1 makes a negative 36. And so that's why I wrote minus 36 right there. Okay. And finally, to simplify my answer, I just have to collect the real parts and say 35 minus 36 is -1. And the imaginary parts, negative 15 minus 84 is minus 99i, and this is it. This is what we call the standard form as a way to represent complex numbers. You always want to represent your answer as a real part plus or minus an imaginary part. So my real part is -1, my imaginary part is negative 99i, and so here I have shown your answer in standard form. So try to simplify all of your answers to standard form. Okay, are there any questions on how we multiply these two numbers? No, still good? All right. So complex numbers have an extra operation that we don't worry about with real numbers, and it's called conjugation. And so if I were to ask you, find the conjugates of these two complex numbers, and we say A is equal to 5 minus 12i, then the conjugate is 5 plus 12i. So two things. We show that we just took the conjugate by putting an over bar above the number like that. So I read this out loud as a conjugate, or you could say the conjugate of a. And notice the only thing that changed was the plus or minus sign on the imaginary part. I don't change the real part. I only change the sign on the imaginary part. That's what makes it a conjugate. So here's the number c, which is 3 plus 4i. C conjugate would be what? Perfect. 3 minus 4i. Is that easy enough? All right. Very good. Here is the big boss of arithmetic. If we want to divide two complex numbers, like I've got a complex number 27 minus 31i and a number 5 minus 12i. How would I do x divided by y? The trick is I have to multiply this by the number 1. Multiplying by 1 doesn't change anything. But specifically, I'm going to choose the conjugate of the denominator divided by the conjugate of the denominator. It's the same as multiplying by 1, right? Y conjugate divided by y conjugate, that has to be 1. So it's not going to change the value of this fraction x over y, but it is going to make it possible to divide these in a way that makes sense. Now, that means we have to do some multiplication problems to get to my division problem in the first place. Like, across the top, I've got x times y conjugate. And that means I draw a box. And x is 27 minus 31i. Y conjugate would be 5 plus 12i. 5 times 27 is 135. And correct me if I make any mistakes, because it's very easy for me to make a mistake. And 5 times negative 31 is going to be negative 155. Hi. 27 times 12 is going to be, thank you, 324, yeah. Negative 31 times 12 is going to be 372. It's negative because of the minus, and then I get an I squared because there's 2 i's. Okay, whew. Big numbers. Very good. So you know that I squared is negative 1. And so where this is a minus 372 I squared, that's the same thing as adding 372. So what I'm thinking about right now is 135 plus 372. That would be 507, I think. Let me say that one more time. The I squared contributes a minus sign, right? but I have another minus sign. So altogether, this is just positive real 372. So if I take positive 372 plus positive 135, that gives me the real part. And this is the real part of just my numerator, because my numerator is where I do x times y conjugate. And that's what we're doing right here. For the imaginary part, I need 324 minus 155. Yep. So to get the real part, I added the top left and bottom right boxes, and to get the imaginary part, I added the bottom left and top right boxes. Hopefully no mistakes. Again, stop me and correct me if you see something wrong. But now let's do the denominator. In my denominator, I will have y times y conjugate. And this is going to be 5 minus 12i times its conjugate, which is 5 plus 12i. Five times 5 is 25. 12 times 12 yeah, that box is going to give me a negative 144i squared. Up here, I've got negative 60i. And here, I've got positive 60i. Now, here is the trick that makes this whole thing work. You know, you might be wondering, why on earth would we multiply by y conjugate over y conjugate when that just makes 2 multiplication problems, right? That's creating so much more work. But the genius of doing this is any time you multiply a complex number times its own conjugate, this happens. That negative 60i and that positive 60i are going to cancel. That's important because now what's remaining is strictly a real number. 25 plus 144 is 169. And that's a real number. Now the great part is I can ask you, what is 507 divided by 169? It's 3. And so your answer is 3 plus 1i. In the end, since my denominator was just a real number, I could take 507 divided by 169 and get 3. And I could separately take 169i divided by 169 and just get I. That's the reason we think what we do. Altogether, that's how you divide 2 complex numbers. So it's a little hassle because in order to divide 2 complex numbers, you have to first remember to multiply by the conjugate of the denominator. And then you have to do 2 multiplication problems, which are already long enough as they are. And then you have to simplify your answer into standard form, like 3 plus I. Questions about how we did that? Anybody? Cool. There will be a question like this on your test where I ask you to divide 2 complex numbers. In my opinion, probably the hardest question on your test. But you can do it. Still a few more topics left today. Like the complex plane. The complex plane is like the xy plane. It's a flat little world where numbers live. And you know, with real numbers, we used a number line, and we said, okay, any real number can fit somewhere on this number line, where 0 is in the middle, the positive numbers are on the right, and negative numbers are on the left, and you can place numbers as dots along my number line. What we do with complex numbers is we say, the real number line is now my horizontal axis, the imaginary number line is now my vertical axis, and if I want to plot a point, like this complex number -3 plus 4i, I find -3 on the real axis and 4 on the imaginary axis, so that this point corresponds to a -3 real part and a +4 imaginary part. This other number, q, is 7 minus 5i. And to plot that, I would find 7 on the real axis and -5 on the imaginary axis. And that's where the number q belongs. And in this way, every single complex number you can think of has a point where it belongs on the complex plane, and every point on the complex plane corresponds to a complex number you could write down by looking at where it is vertically and horizontally. So, if I ask you to take the absolute value of a complex number, the absolute value is the distance, the shortest distance through the complex plane from your number to 0. So if I wanted, for example, the absolute value of p, that would be the shortest distance from p to 0. Basically, what's the length of that line segment? That's the absolute value of p. Yeah. Now you see why I started off today's lecture talking about the Pythagorean theorem. Is because I could draw a little right triangle here, a little ghost right triangle. And the bottom side length of this right triangle is 3. The vertical side length of this right triangle is 4. And if I want to find the absolute value of p, that's just the length of the hypotenuse. And my Pythagorean theorem says 3 squared plus 4 squared has to equal the length of my hypotenuse squared. And 3 squared plus 4 squared is 9 plus 16, so it's 25. And so 25 is equal to the length of my hypotenuse squared. And so that means the absolute value of p is 5. Yeah. Since we define absolute value as the distance from 0, we have to use the Pythagorean theorem to find the absolute value of complex numbers that lie out there in the plane. Let me switch colors and we can do absolute value of q. Well, maybe I'll save this because you can write a formula down. You don't have to draw the triangle every time and think about it that way. The formula, and again, this is a formula because of the Pythagorean theorem, right? If I say A is my real part and B is my imaginary part, then I write a squared plus b squared equals the absolute value of z squared. And that means to get the absolute value of z, I just have to take the square root of a squared plus b squared. And so that is always true. It's a weird formula for the square root, but it comes from using the Pythagorean theorem on these distances from 0 in the complex plane. So now if I wanted to take the absolute value of q, this would be the square root of 7 squared plus negative 5 squared. It's the real part squared plus the imaginary part squared. And that is the square root of 49 plus 25, which would be 74 maybe?
Yeah.
And we might be able to simplify this. I don't know. If I wanted to find out, can I simplify that square root? I'm thinking about the prime factorization of 74. So I think about 2 times 37. Okay? What about 37? Is it divisible by 2? No. Is it divisible by 3?
No.
The number 37? Is it divisible by 5? No. Is it divisible by 7?
No.
No, because 35 is divisible by 7, but 37 is not. And I can stop, because 7 squared is 49 anyways, right? I could actually only ask about 2, 3, and 5. And so the prime factorization of 74 is just 2 times 37. And that means I can't simplify the square root, right? It's already as simple as it gets because I don't have any factors squared. And so for my answer, I write that the absolute value of q is the square root of 74. Okay. If I have powers of a complex number, I'll tell you this very briefly. 3 minus 4i squared is just 3 minus 4i times 3 minus 4i. And you can do this the same way you would multiply. If you've got the 3 power, the 4 power, you would just continue to multiply. It works the same way multiplication works. So I don't have to show you another example. We only have 17 minutes left, so I'll move on. If I have a negative 1, right? A negative exponent tells you to take the reciprocal. And so this would be 1 divided by 3 minus 4i. And whenever you divide by a complex number, we multiply by the conjugate of the denominator on the top and on the bottom. This time, my numerator is easy because it's just 1 times 3 plus 4i. To get my denominator, I have to multiply 3 minus 4i times 3 plus 4i. Three times 3 is 9. 4 times 4 is 16. This is negative 12i. This is positive 12i. We're happy because these cancel. Of course, they cancel by design. That's the reason we're multiplying by conjugates. And then what I'm left with is 9 plus 16, which is 25. My answer in standard form is 3/25 plus 4 over 25i. A real part plus an imaginary part. That's your standard form. Again, I'm annoying you because this is important. Why did I say 9 plus 16 and not 9 minus 16? Because I squared is the same as negative 1. two negatives make a positive, and that's why I said 9 plus 16. Okay. Almost done here. We got a little abstract discussion to work through. I love asking closed under questions. And I'll fill in some stuff that we already discussed. Like, we already said that the natural numbers were closed under addition and multiplication, but they were not closed under subtraction or division. The integers were nice because the integers were closed under subtraction. You could subtract two integers and always get an integer back. That wasn't true for the natural numbers, but it is now true for the integers. What was great about the rational numbers is whenever we decided to include fractions, that actually makes the rational numbers closed under division. If you divide two fractions, you just multiply by the reciprocal, and you always get a rational number back. That's cool. The only thing you can't do is divide by 0, but that's the only exception, and so we can ignore it and still say we're moving on, we're moving forward. Everyone knows you can't divide by 0, but that's okay. The real numbers are, in fact, closed under all four operations, meaning if you want to add, subtract, multiply, divide any two real numbers, you will still end up with a real number. And the rest I want to fill in together. So what about prime numbers? Are prime numbers closed under addition? Who thinks yes? And who thinks no? Yeah. So when I think about prime numbers in addition, think about 3 plus 5. 3 and 5 are primes, but when we add them together, we get 8. And 8 is not a prime, and so that means we're not closed under addition. Prime numbers are not closed under subtraction for the same reason. They're not closed under multiplication because if you multiply two prime numbers, then you get a composite number by definition, right? The definition of a prime number is that it has like no factors besides 1 in itself. And of course, prime numbers are not closed under division because neither are the natural numbers. Prime numbers are not a nice set of numbers to deal with in algebra. Irrational numbers. This is an interesting question. It's something I had to think about for a moment. Are the irrational numbers closed under addition?
Yes.
So if you add together two irrational numbers like pi plus square root of 2, are you going to always get an irrational number back?
I have no idea.
Yeah. So it turns out the answer is no. And I'll tell you why I know for certain that this is not going to work. First of all, for addition, square root of 2 is an irrational number. The negative square root of 2 is an irrational number. And, in fact, square root of 2 plus 3 is still irrational. Adding 3 does not save it from being irrational because you still have an infinite decimal expansion with no repetition. So what happens if I add these two irrational numbers together? I get 3. But 3 is perfectly rational, which means we're not closed under addition or subtraction. Multiplication is even easier to see and understand because square root of 2 is irrational. Square root of 2 is irrational. But when I multiply those two, I get a rational number. And so that's why we're not closed under multiplication. For division, think of square root of 2 divided by square root of 2. It's 1, right? It doesn't work. So the irrational numbers, we don't think about them very much as a set of numbers on their own, except in the degree that the irrationals complete the real numbers when you take them together with the rational numbers. because they don't have nice algebra properties. Are the imaginary numbers closed under addition? Yeah. If you add two imaginary numbers, you get an imaginary number. Are they closed under subtraction? Yes. If we subtract two imaginary numbers, we always get an imaginary number. Are they closed under multiplication though? What about I times I? That's multiplying two imaginary numbers, but you get -1, and -1 is a real number, not an imaginary number. And likewise, they're not closed under division. Complex numbers, like we saw today, you can add, subtract, multiply, and divide complex numbers, and you always get a complex number back. Remember that the complex numbers include the real numbers. Anytime you have a real number, like the number 3 is a real number, that is the same thing, right? So the complex numbers include the real numbers as part of the set of complex numbers. That was something I showed you. Again, as part of our Venn diagram, I showed you the Venn diagram where the complex numbers include all of the real numbers as part of the complex number set. Complex numbers, that's the big set of numbers. Complex numbers have a cool property that the real numbers don't have. The real numbers are not closed algebraically. For example, if I come up with an algebraic equation like this, and I didn't type this out, but I'll tell you, an algebraic equation is an equation where you have a polynomial equals a polynomial. And you can always rewrite this algebraic equation so that you have a polynomial equals 0 if you subtract the right terms. What I mean by a polynomial is a complex number coefficient times a variable raised to a natural number power. And you can add as many of those terms as you want together, and the resulting expression is called a polynomial. So this, for example, is a polynomial equal to 0. So that makes this an algebraic equation. And one thing that's important is that the solutions, well, let me say this. There are two solutions to this equation. Because 2 is the largest power of x. If you want to know how many solutions are there to an algebraic equation, look at the largest power of your variable. That's the answer. Okay? So let me give you a little example, a little side example. If I tell you this, how many solutions are there to this equation? 5, because 5 is the largest power. That's a neat property of algebraic equations, and we'll talk about this later in the semester too. But if you look at the largest power, that's how many solutions there should be. But these solutions are not always real numbers. But these solutions are always complex numbers. Which means they could be real, but you definitely have complex solutions. In this original equation that I wrote down, the solutions to this equation are x equals I and x equals negative I. That's two solutions to this equation, and they're not real, but they're complex. And that's why we say the complex numbers are closed algebraically. Not only are they closed under addition, subtraction, multiplication, division, but also anytime you write an algebraic equation, you always get complex number solutions. For this other equation that I wrote, x to the fifth plus x equals 0, I don't know the answers off the top of my head, but we can find the answers. Here's x to the fifth plus x equals 0. So there's 5 complex number solutions, right? If it's a real number solution, real numbers are also complex numbers. 0 is a complex number. It lives in the complex plane, right? But also 4 more numbers that are strictly complex. And so that's, again, why we like the complex numbers in algebra, is because we can always find solutions in terms of complex numbers. That's a good thing. And that's it.